In 1939, Albert Einstein published a paper arguing that black holes were physically impossible. That same year, just months later, Robert Oppenheimer published a paper proving that they were inevitable. Two of the greatest minds in physics, alive at the same time, looking at the same equations, reaching opposite conclusions. And honestly, we still haven't fully settled this. Not the way you might think, because just a few days ago, a team of researchers published a study showing that the supermassive object at the center of our galaxy, the thing we've been calling a black hole for decades, can be explained just as well by something completely different: a massive core of dark matter particles. No event horizon, no singularity, no black hole at all. So let's actually do this properly. Let's look at what black holes supposedly are, why almost everyone believes in them, and then give the alternatives the fairest hearing we can. Because if there's even a chance we've been wrong about this, that matters. First, some history, because it changes how you think about this whole thing. The idea of an object so massive that light can't escape goes all the way back to 1783. A guy named John Michell did the math using Newtonian physics and proposed what he called dark stars. Interesting idea, wrong framework, but weirdly prescient. Then nothing happened with it for over 100 years. When Einstein finished general relativity in 1915, Carl Schwarzschild solved Einstein's equations within months and found something strange. There was a radius around any mass where the math broke down, a boundary. Cross it, and according to the equations, nothing comes back. Not light, not matter, nothing. But nobody knew what to make of it. Most physicists, including Einstein himself, thought it was just a math glitch, an artifact of the equations, not something that could actually exist in nature. For decades, that was the dominant view. Arthur Eddington mocked the idea that stars could collapse into such things. Einstein actively tried to disprove them, and then Oppenheimer and Snyder came along in '39 and showed mathematically that when a massive enough star runs out of fuel, the collapse doesn't stop. There's no force in known physics strong enough to prevent it. The star just keeps falling inward, past that critical radius, and an event horizon forms. Einstein, to his credit, called it an epoch-making result. But even then, most physicists weren't convinced. What really changed things was Roger Penrose in 1965. He proved something that Einstein and everyone else had been hoping wasn't true. Singularities, these points of infinite density at the center of a collapsed object, weren't exotic special cases. They were generic. If general relativity is correct and you have enough mass in a small enough space, a singularity forms. Period. It's not a maybe. It's a mathematical inevitability. Penrose won the Nobel Prize for this in 2020, and then John Wheeler coined the term black hole in 1967, which honestly did more for public awareness than any equation ever could. So that's how we got here theoretically. But theories are just theories until you test them. So what's the actual evidence? The strongest case comes from the center of our own galaxy. For over 20 years, two independent teams have been tracking stars orbiting an invisible object called Sagittarius A star. The most famous of these stars, called S2, completes an orbit every 16 years. At its closest approach, it screams past at 7,650 kilometers per second. That's 2.5% the speed of light. From its orbit, you can calculate the mass of whatever it's orbiting. 4.3 million times the mass of our sun, all crammed into a space smaller than our solar system. Way smaller, actually. The object's boundary has to be within about 44 million kilometers. For reference, Mercury orbits the sun at about 58 million kilometers. So we're talking about 4 million suns packed into a space smaller than Mercury's orbit. Andrea Ghez and Reinhard Genzel shared the 2020 Nobel Prize for this work. The precision of these measurements is extraordinary. They can track stellar positions to within 300 microarc seconds. That's like seeing a coin from 10,000 kilometers away. But here's the thing. Those orbits only tell you that something extremely massive and extremely compact is sitting there. They don't tell you it has an event horizon. They don't tell you it has a singularity. Any object with that mass packed into that volume would produce the exact same stellar orbits. Then came the Event Horizon Telescope. In 2019, the EHT collaboration released the first image of a black hole shadow in the galaxy M87, a supermassive object, 6.5 billion solar masses, 55 million light-years away. They linked radio telescopes all over the planet to create a virtual telescope the size of Earth and captured a bright ring of light with a dark center, the shadow. In 2022, they did the same for Sagittarius A star, our galaxy's central object. The shadow's size and shape match what general relativity predicts for a black hole of that mass. That's significant. But, and this is important, a study published in 2024 by Pell and colleagues showed that a dense core of fermionic dark matter, with no event horizon at all, would cast a nearly identical shadow when surrounded by an accretion disk. Same ring, same dark center, same size. Observationally indistinguishable with current technology. Then there's gravitational waves. In 2015, LIGO detected ripples in spacetime from two objects spiraling into each other and merging 1.3 billion light-years away. The signal matched general relativity's prediction for two black holes, about 30 and 35 solar masses, smashing together. The crucial part is the ring down, the signal the merged object emits as it settles down. For a black hole, general relativity predicts very specific frequencies, like a bell with a known tone. And the observed ring down matched those predictions beautifully. Over 90 merger events have been detected since then, and all of them are consistent with black holes. Now, this is where gravitational waves actually do narrow things down compared to the other evidence, because some alternatives predict different ring down signatures. Simple gravastars, for example, were tested against the first LIGO detection in 2016 and found to be inconsistent. Their predicted ringing didn't match what LIGO heard, so we've got stellar orbits, shadow images, and gravitational waves. Three independent lines of evidence. That's a strong case, but it's not the same as proof, because here's the uncomfortable part. Every one of those observations is also consistent with at least one alternative explanation, and the most credible alternative got a major boost just days ago. The fermionic dark matter core model proposes that what sits at the center of our galaxy isn't a black hole at all. It's an incredibly dense ball of dark matter particles. These particles are fermions, meaning they obey the Pauli exclusion principle, the same quantum rule that keeps electrons from all piling into the same state. This quantum pressure, called degeneracy pressure, is what prevents the object from collapsing into a singularity. Same basic idea that holds up white dwarf stars, just scaled up enormously and applied to dark matter instead of regular matter. The model, developed by Arguelles, Crespi, Pell, and others, predicts a dense central core with a radius comparable to where a black hole's event horizon would be, surrounded by a diffuse halo that extends throughout the galaxy. No event horizon, no singularity. And critically, it fits the observed orbit of the S2 star just as well as the black hole model does. Bayesian statistical comparison between the two models shows they're essentially tied with current data. We actually covered a related angle on this channel before, the idea that the Milky Way center might not be what we've assumed. This new research takes that further, but it gets more interesting. This dark matter core model doesn't just explain what's at the galactic center. It also reproduces the Milky Way's rotation curve, the way stars at different distances from the center orbit at different speeds. Standard cold dark matter models have trouble with this. The fermionic model handles it naturally. One framework, two explanations. That's efficient. Now, I want to be fair to skeptics on both sides here. If you're skeptical of black holes, these alternative models give you legitimate scientific ground to stand on. This isn't fringe stuff. It's published in the monthly notices of the Royal Astronomical Society, one of the oldest and most respected astronomy journals. If you're skeptical of the alternatives, that's also reasonable. The black hole model is simpler, it's been around longer, and it fits a wider range of data across different mass scales. The honest answer is that for stellar mass black holes, the ones LIGO detects, the evidence is very strong, somewhere around 85 to 90% confidence, if you want to put a rough number on it. The gravitational wave ring-down signatures are hard to replicate with alternatives, and most alternatives for that mass range have been ruled out or shown to be unstable. For supermassive objects like Sagittarius A star, it's lower. maybe 70 to 80%. The fermionic dark matter alternative is genuinely viable. The shadow images don't uniquely prove an event horizon exists, and we don't yet have gravitational wave detections from supermassive mergers because those waves are at frequencies too low for LIGO. We need the LISA space mission for that, and that's not launching for years. So what would it take to actually settle this? There are a few specific things that would push the answer one way or the other. First, photon rings. A real black hole should produce not just a single ring of light, but nested rings, like an infinite series of reflections. Light orbiting the black hole once, twice, three times before escaping. The fermionic dark matter model predicts no such nested rings. If next-generation telescopes can resolve those secondary rings, that's a strong point for black holes. If they're absent, the alternatives get much more interesting. Second, gravitational wave echoes. If the merged object in a LIGO detection has any internal structure, some kind of surface or boundary instead of a clean event horizon, the gravitational waves should bounce around inside and produce echoes, faint repeated copies of the ring-down signal. Searches through LIGO data have found no echoes so far. That's consistent with true black holes, but the detectors might not be sensitive enough yet. Third, surface emission. A real black hole has no surface. Anything falling in just disappears past the event horizon. But if the object has any kind of physical boundary, matter hitting that boundary should produce thermal radiation. If we ever detect that kind of emission from something we thought was a black hole, the game changes completely. We're probably looking at the 2030s or 2040s before these tests become decisive. The technology isn't quite there yet, but it's getting close. And I think there's something worth acknowledging here that often gets skipped. We could be wrong in a way we haven't even considered yet. All of the alternatives I've described, the fermionic cores, the gravastars, the boson stars, they're all built within our current theoretical frameworks, quantum mechanics and general relativity. But we know those two theories are fundamentally incompatible at the smallest scales. Whatever quantum gravity actually looks like, and nobody knows yet, it might change what happens at the center of these objects in ways none of our current models predict. Maybe there are no singularities and no event horizons, but also no dark matter cores. Maybe it's something we literally don't have the physics to describe yet. That's not a cop-out. That's an honest statement about where we are. General relativity has been tested brilliantly at large scales. Quantum mechanics has been tested brilliantly at small scales. Neither has been tested where they overlap, in the extreme gravity at the heart of these objects. That's the frontier. What I find genuinely exciting about this moment is that we're not just debating philosophy, we have specific concrete observations that will settle this. Photon rings, gravitational wave echoes, surface emission tests, these aren't hypothetical, someday experiments. The instruments are being built right now. Within our lifetimes, we will probably know whether the darkest objects in the universe are truly what we've believed for 60 years, or something nobody expected. Einstein thought they were impossible. Oppenheimer proved they were inevitable. Penrose showed singularities couldn't be avoided. And now in 2026, a team of researchers is saying maybe we should reconsider the whole thing. That's not a failure of science. That's science doing exactly what it's supposed to do. Want more of the latest discoveries that are rewriting what we thought we knew? There's always another one waiting.